You know, I was sitting in a coffee shop the other day just watching people, and everyone is just glued to their phone.
Of course.
You press the side button, the screen.
Good engineering, isn't it?
It has to be.
It is designed to look simple, so you never ever have to think about the absolute chaos happening just underneath the glass.
Exactly. And, you know, usually I'm happy to be tricked. I'm happy to just let it work. But today, we are pulling back the curtain.
We are.
We have a stack of documents here. Technical schematics, board layouts, repair guides, all for the iPhone 13 series. And looking at this, simple is the last word I would use.
Simple definitely left the building a long time ago.
It really did. We're not just looking at a battery connected to a screen anymore.
Not at all.
We are looking at what I can only describe as a completely redesigned nervous system. The way the iPhone 13 handles power compared to, say, the iPhone 12. It's like a species jump.
It really is. It's a fundamental architectural shift. If you are a repair technician or an engineer coming from the 11 or 12 and you open up a 13 without reading this stuff,
You'd be lost.
you are going to be completely lost. The rules have totally changed.
So our mission for this deep dive is to map out that new nervous system. We are going to look specifically at the main power line, the jugular vein of the phone, if you will, and figure out how this thing actually drinks and manages its energy.
Right.
Because according to these sources, the old days of just a positive wire and a negative wire, they're dead and gone.
Long gone. The complexity has skyrocketed because, well, the demands have skyrocketed.
So let's start with the most obvious clue in the paperwork, the name. The name of the power line itself. In older models like the iPhone 12, this line had a pretty standard name, right?
Right. It was usually labeled PPBATT-VCC, which is just engineering shorthand for power path, battery, voltage common collector. Pretty standard stuff.
But in the iPhone 13 schematics, that label has mutated. It's longer now.
It is.
It's now PPBATTTCCBPIC.
And in the world of schematics, an extra suffix like that isn't a typo. It's a roadmap.
Yeah.
That BPIC at the end is the key to this whole mystery we're exploring.
Okay, let's unpack that. What does BPIC stand for?
It stands for Boost Power IC.
Boost Power IC.
And just by seeing that in the name, it tells us the battery isn't just dumping raw voltage into the system anymore. It's being routed, managed, and manipulated by a new sophisticated layer of silicon.
So instead of a direct fuel line from the tank to the engine, it's more like a managed intake system with a turbocharger.
That's a fantastic analogy.
Yeah.
The architecture has shifted from a direct connection to a committee approach.
A committee, I like that.
The power doesn't just go to the phone, it goes to a specific trinity of chips that decide what to do with it.
The Trinity. Okay, let's meet the committee members because their interaction is honestly fascinating. We have the heart, the brain, and the newcomer.
Exactly.
Let's start with the newcomer, since that's what the name change is all about. This is the U4200 chip.
Correct. The U4200. This is that boost power IC. Now, this is crucial context. If you look at the board layout of an iPhone 12 Pro Max or an 11 or an X, you simply will not find this chip doing this job.
It's not there.
It does not exist. It is a brand new addition specifically for the iPhone 13, 13 Pro, and Pro Max, and it sits directly on that main power line.
But why? I mean, Apple is famous for being ruthless about saving space. They remove headphone jacks, they shrink SIM trays, they fight for every single millimeter inside that chassis. They wouldn't add a whole new chip unless they absolutely had to. What problem is this U4200 solving?
It's solving the problem of stability under extreme load. Think about what we ask our phones to do now. We have 5G modems pulling massive data streams. We have promotion displays refreshing at 120 times a second. We have the A15 processor just hammering away at neural engine tasks. These things create massive, sudden spikes in power demand.
It's like turning on a hairdryer in a house with bad wiring. The lights flicker.
Exactly. In a phone, if the lights flicker or the voltage drops too low, the phone crashes. It just shuts off. The U4200 is there to prevent that. It essentially boosts and stabilizes the voltage from the battery before it gets distributed to the rest of the system. It ensures that no matter how hard the processor hits the gas, the fuel pressure stays constant.
So it's a gatekeeper, a bouncer at the club ensuring nobody messes up the vibe inside.
A very, very strict bouncer. In fact, for technicians, this chip has become the primary diagnostic checkpoint.
Really?
If you have an iPhone 13 that is completely dead, won't turn on, won't charge, you don't just check the battery terminal anymore. You go straight to the U4200.
The notes here mention a specific test that I found really interesting. It mentions pins C4 through M4.
Right. This is Technician's Insight 101 for the iPhone 13. The U4200 is a ball grid array chip, so it sits on these little balls of solder.
Okay.
Specific pins, labeled C4 through M4, are the input. If you probe those points, the voltage reading must match the battery voltage exactly.
Exactly. Not just close.
It has to be identical.
Yeah.
If you put your probe there and you get 0, or you see a significant drop compared to what the battery is putting out, you have found your problem instantly.
Wow.
It tells you there's a physical break in the line between the battery and this new chip.
It's like checking for a pulse at the neck. If you don't find it there, it doesn't matter what the rest of the body is doing. The energy never made it out of the gate.
Precisely. So that's the newcomer, U4200. But it's not working in a vacuum. It has to coordinate with the brain of the charging operation.
And this is the chip with the surprisingly dramatic name, the Rubicon?
The Rubicon, U4000.
I have to stop you there. Do we know why it's called Rubicon? Is that an actual crossing the Rubicon reference?
In engineering, these code names are rarely accidental. Crossing the Rubicon implies a point of no return, right? A critical decision point.
Sure.
In this context, the U4000 is the ultimate authority on charging. It replaces the older Yangtze chip from the iPhone 12 era. Now, Yangtze was a fine chip. It did its job. But Rubicon is a different beast entirely.
How so? Is it just handling more wattage for faster charging, or?
It handles the power, yes. It controls both wired lightning charging and wireless MagSafe charging. But the real shift here is its place in the hierarchy.
The hierarchy.
Yeah. Usually we assume the main processor, the A15 Bionic, is the boss.
Right.
It's the CPU. It runs iOS. It controls the phone. We think of the CPU as the brain that controls the hand.
Of course. The CPU tells the screen what to show, it tells the speakers what to play, so naturally it should tell the battery what to do.
That's the assumption. But when it comes to the power system in the iPhone 13, the A15 is not the boss.
It's not.
The Rubicon U4000 is the master.
Wait, really? The main processor isn't the one talking to the battery?
No. The Rubicon acts as the master of communication specifically for this power loop. It holds the direct conversation with the battery. The A15 is effectively out of the loop for these micro decisions.
Why would Apple do that? Why cut the main brain out of that loop?
Latency and safety. The A15 is busy. It's rendering 3D graphics, processing background updates, running the OS. If something goes wrong with the battery, say a thermal runaway or a voltage spike, you need a reaction time measured in microseconds.
Right.
You can't wait for the CPU to finish rendering a frame of a video game to decide to cut the power.
Ah, I see. It's like a reflex. You touch a hot stove, your spinal cord pulls your hand back before your brain even realizes you're burned.
Exactly. The Rubicon is that spinal reflex. It challenges that classic idea that the CPU controls every single process. In this specific power loop, Rubicon is the one calling the shots.
So let's talk about this conversation between the Rubicon and the battery. I think most of us picture a battery as just a chemical bucket. It's either full or empty. How much is there really to talk about?
A surprising amount. And this brings us to the connector itself, J11000. If you look closely at the schematic, it's not just a big red wire and a big black wire.
There's more.
There are specific, delicate data lines running between the battery and the board.
And these lines are speaking what language?
They're speaking I2C.
I2C. Okay, we see this acronym a lot in electronics. For anyone listening who might not be familiar, can we just strip this down? What is essentially happening on an I2C line?
Think of I2C as a very strict synchronized dialogue. To have this dialogue, you need two fundamental things, a clock and data.
A clock. Like to tell time.
No, like the metronome. That's the SCL line serial clock. The master device, which in this case is a Rubicon chip, generates a steady pulse. Tick, 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 tick.
It sets the tempo.
It sets the speed of the conversation. It tells the other devices when to listen.
And the data line.
That's the SDA serial data. That's where the actual information travels. But here's the key to that master-slave relationship in I2C. The battery, which is the slave device, is not allowed to speak unless the Rubicon asks it to.
So the battery can't just shout, hey, I'm overheating whenever it wants.
It has to wait for its turn. The Rubicon sends a clock pulse, addresses the battery, and says, report status. Only then does the battery send data back on the SDA line. It's a very controlled hierarchical loop.
And what exactly is it reporting? Is it just the percentage? I'm at 80%.
It goes much deeper. It's reporting cycle count, precise temperature, current flow, and the status of the internal cells. This is where the sense lines come in.
The notes mention V-cell and V-cell P.
Right. These are analog sense lines. Now, this is different from I2C. I2C is digital ones and zeros. The V-cell lines are analog. They're measuring raw voltage curves directly from the battery cells.
Okay.
And there's this tiny detail here that I love because it shows the level of precision Apple is aiming for.
Which detail is that?
The path of the negative sense line, VCell. It doesn't just run straight into a chip. It passes through a specific 20K resistor first.
A 20K resistor. Okay, resistors usually limit current. Why put one on a sensing line?
It acts as a pull-down resistor to establish a clean, low state. Basically, it just cleans up the signal. It conditions the signal before it hits that new U4200 boost chip we talked about. It ensures the chip is reading a precise, noise-free voltage reference.
So it's the difference between guessing the temperature of water by sticking your hand in versus using a calibrated thermometer.
That's it, exactly. So the U4200 isn't just boosting power blindly, it's listening. It's making decisions based on this highly conditioned, precise health data coming from the battery.
Amazing how much thought goes into just reading a voltage.
Okay, so we've covered the newcomer, U4200, and the brain, Rubicon U4000. We need to address the third member of the committee, the heart, the classic power management IC, or PMIC, U3100. This is the workhorse. This is the chip that takes that raw power and chops it up into all the little voltages that the rest of the phone needs. 1.8 volts for memory, 0.8 volts for the CPU, 2.7 for the camera.
Right, but looking at the schematics, the PMIC doesn't get the same VIP treatment that the other two chips get. Its path is a bit of a detour.
It is. While power rushes straight to the Boost and Rubicon chips, the path to the main PMIC, specifically to pin E12, has to pass through a gatekeeper, a series resistor labeled R3702.
R3702. This seems to be a recurring theme. These tiny little resistors with massive responsibilities. What does R3702 do?
It's a current sense resistor. Basically, the system measures the tiny voltage drop across this resistor to calculate exactly how much current is flowing into the PMIC.
So it's like a toll booth that counts the cars passing through.
A very precise toll booth. And if that toll booth collapses,
Uh-oh.
then the system loses its ability to gauge power consumption. And this is a very common failure point that technicians can miss. If R3702 is damaged from a drop or a short or just heat stress, its resistance value can stretch.
Stretch? You mean the value physically changes?
Exactly. It might go from, say, 1 ohm to 100 ohms. If that value changes, the math the chip uses to calculate power is now completely wrong.
And if the math is wrong, the phone just gets confused.
Confused is putting it mildly. The phone might not turn on at all because it thinks there's no power flowing. Or, and this is stranger, the phone will boot up, but it can't read the battery status. You'll see an empty battery icon, even if the battery is 100% full.
That's a nightmare.
It is because the PMIC effectively doesn't know how much electricity it's using.
What a nightmare diagnostic scenario. You'd replace the battery, still empty, replace the screen, still empty, and it turns out to be this tiny speck of a resistor on the logic board.
That's the reality of modern electronics repair.
Yeah.
It's rarely the big components anymore. It's the support infrastructure.
Speaking of infrastructure, we have to talk about the physical geography of these chips, because knowing the schematic is one thing, that's lines on paper, but finding these things on the actual board is another. And this is where the iPhone 13 lineup splits in two.
Right, you have the standard iPhone 13, and then you have the Pro models. Mm-hmm. And the layout difference is drastic.
The standard 13 is described in the notes as a single-layer face. That sounds approachable.
It is. It's lovely if you're a technician. It means the board is effectively flat. All the major players we just talked about, the battery connector, U4200, Rubicon, the PMIC, they're all on the same side of a single board. You can visually trace those red power lines. It's a 2D map.
But the Pro models, the Pro and Pro Max, they use the sandwich.
The sandwich board. This is where Apple's engineering gets aggressive. To pack in the triple camera system, the LiDAR scanner, all the extra GPU cores, they literally ran out of floor space.
So they built a second floor.
They built a second floor. They stacked 2 circuit boards on top of each other.
A double-decker bus.
Exactly.
Hey.
But think about the logistics of that. We just talked about all these delicate data lines, the I2C clock and data, the power rails. They might start on the top board, but some of the chips they need to talk to are on the bottom board.
So they have to commute between floors.
They do. And the elevator is the interposer. It's a connecting layer, essentially a frame of tiny solder pillars that connects the ceiling of the bottom board to the floor of the top board.
Solder pillars, that sounds brittle.
It is. Solder is a metal alloy, but it's soft. It can crack under stress. If you drop your iPhone 13 Pro, a hard impact on concrete, the boards themselves might be fine, the chips might be fine, but the interposer connections can fracture.
And if that fracture happens on, say, the I2C line,
the conversation stops. The Rubicon gets cut off from the battery. The brain gets cut off from the energy source. The phone is dead. It's a bridge-out scenario.
That seems like a massive reliability risk. How does a technician even find that? You can't see the interposer. It's buried in the middle of the sandwich.
Traditionally, you'd have to perform what we call major surgery. You'd have to put the board on a heater, melt the solder frame, and split the sandwich just to look inside. It's incredibly risky.
I can imagine.
You could overheat the CPU, you can knock off other components, you can kill the phone just by trying to diagnose it.
But the notes suggest Apple anticipated this. They left a back door.
They did. And honestly, it's a brilliant piece of design for diagnostics. On the Pro models, right near the battery connector, there are these tiny exposed conductive spots.
Test points.
Yes. Labeled TPV-BATT, TPI2CSCL, and TPI2CSDA.
So they brought the internal signals all the way out to the surface.
Exactly. These points are accessible without splitting the boards. They let a technician touch a probe to the surface and listen to the heartbeat of the phone from the outside.
So you can check if the Rubicon is sending that clock signal.
You can see it pulsing. If you get a signal at TPI2CSCL, you know Rubicon is alive. More importantly, you know the interposer connection for that line is intact. You can verify the voltage at TPV-BATT. It lets you diagnose a severed interposer connection in seconds instead of hours of risky work.
It essentially answers the question, is this a board failure or just a connection failure?
Right. It balances the extreme engineering density of the sandwich board with the practical reality that these things get dropped and need to be fixed. It's a bit of a nod to the repair community.
So, stepping back from the microscope for a second, we've gone from a simple battery icon to this complex committee of chips, the heart, the brain, and the newcomer.
U3100, U4000, and U4200. Yeah.
We've seen how they negotiate power using this strict I2C protocol, and how physically the Pro models take this risky three-dimensional journey through the interposer.
It really paints a picture of a decentralized system. That's the key takeaway for me.
Decentralized.
The iPhone 13 architecture moved away from a centralized power model, where the CPU does everything, to a decentralized one where these dedicated chips handle the heavy lifting.
They manage the stability, they handle the boost, they maintain the communication lines.
And they do it all autonomously.
It really does change how I look at the device. You know, it's sitting there on the table right now, screen off, looking completely asleep. But inside, that Rubicon chip is wide awake.
It is.
It's the master. It's pinging the battery, checking the health, managing the voltage, having this whole conversation.
All completely unbeknownst to the A15 processor that we usually think of as the smart part of the phone. The CPU is effectively asleep, while the power system is running its own marathon.
It raises a bit of a provocative question, doesn't it? If the battery charging system is sophisticated enough to act as a master, holding its own secret conversations and managing critical variables without the main CPU even knowing, what other subconscious processes is our phone running right now that we and the main processor are completely unaware of?
That is a question that opens up a whole other layer of schematics. But for the power system, at least, we know who is really in charge.
Something to think about the next time you plug in. That's it for this deep dive into the nervous system of the iPhone 13. Thanks for listening.
All right, let's get into it. Today we're going to go deep under the hood of the iPhone 13. We're looking at something you're using every single second you hold your phone, but probably never even think about. Its power system. Specifically, we're going to trace the path of what Apple completely redesigned, what we're calling the new power highway. Look, this isn't just some minor update or a tiny component change. Apple basically went back to the drawing board here. They created a totally new architectural shift in how power gets from the battery to, well, everything else in the phone. So think of this as a guided tour. We're going to follow that exact path right from the beginning. So here's our game plan. First, we'll check out the new power map. Then we'll follow the journey right from the battery. After that, we'll meet the 3 power bosses that run the whole show. We'll also see how the Pro models make things a bit more complicated. And finally, we'll talk about why any of this actually matters. Okay, our first stop is kind of hidden in plain sight. It's all in the name. You see, in electronic schematics, the names of the circuits tell you a story. And for the iPhone 13, the main power line got a brand new name. PP_BATT_VCC_BPIC. And that change alone is a huge clue that things are very, very different this time around. So the key here is that little bit at the end, BPIC. In all the older phones, this main line was just called PP_BATT_VC. That new part, BPIC, actually stands for Boost Power Integrated Circuit. It's our very first signal that there's a new, specialized player on the field, and it completely changes how power is managed. All right, let's move on to our next stop and see where this is all going. We're starting our journey right at the source, the single point where every drop of power for your phone comes from, the battery connector itself. Now, this connector, it isn't just a simple plus and minus plug. It's more like a little command center. You've got your main power line, sure, but you've also got data lines for communication and even sense lines that are constantly checking on the battery's health. It's a nonstop conversation happening, not just a simple flow of electricity. And right after the power leaves that connector, we see it. The single biggest change in this whole design. The main power highway immediately splits into two completely separate paths. You can kind of picture it like a big river forking right after it leaves a dam. And this is the main takeaway right here. One source, but two distinct highways. Instead of just sending all the raw battery power to one central manager like they used to, Apple now splits the workload. And why would they do that? Well, it's all about efficiency. When you send power to specialized managers, they can do their job better, which means less energy wasted as heat, and, you guessed it, better battery life for you. So who's in charge of these new highways? Let's meet the three main characters in this whole story. The integrated circuits, or ICs, that act as the bosses of this entire power system. First up, we've got the newcomer, U4200. This is that boost power IC we mentioned earlier, the BPIC. It's the first of its kind in any iPhone, and its one and only job is to take that raw battery voltage and efficiently boost it or increase it for parts of the phone that need a little more juice. Having a dedicated specialist just for this one job means it gets done way more efficiently. Next, meet U4000. This chip used to just handle charging, but now it's gotten a big promotion. It still manages all the power coming in from your charging cable or wireless charger, but now it also has a critical new role. It's the communications chief, talking directly with the battery. And finally, we have the heart of the whole operation, the main power management IC, or PMEC. What's interesting is that it doesn't get raw battery power anymore, no. It gets perfectly conditioned, pre-managed power from the other two bosses. And its job is to then distribute that clean power to absolutely everything else. The CPU, the screen, the cameras, the whole show. So let's zoom in on that new role for U4000. It's now the I2C master. What on earth does that mean? Well, it means it's now in charge of that data conversation with the battery. Before, the main CPU, the brain of the whole phone, had to do this job. By giving this task to a specialist chip, the CPU is freed up to do what it does best, run your apps, and make your phone feel fast. It's a really smart engineering move. Okay, so just when you think you've got it all figured out, things get even crazier when we look at the Pro models. The actual physical design of their logic board creates a whole new challenge. It's what technicians call the sandwich board. So on the left, you can see the logic board from a standard iPhone 13. It's one single letter, pretty straightforward. But then look at the board from an iPhone 13 Pro on the right. Whoa, that's actually two separate circuit boards stacked right on top of each other and soldered together. It's a great way to save space, but it creates a massive problem. How do you get power and signals from one layer to the other? The answer is a clever little component called an interposer. You can basically think of it as a bunch of tiny electrical bridges, or maybe elevators, that connect the top and bottom boards. It's what allows those power highways we've been following to travel between the two layers of the sandwich. So, if you're a repair technician, how do you diagnose a problem on one of these boards without doing the incredibly risky surgery of splitting them apart? Well, the answer is right here. Test points. These are tiny little accessible pads on the board that act like windows, letting you peek inside and measure the crucial signals that are flowing through that hidden interposer. It's a truly elegant solution to a really complex problem. Okay, so we've looked at the new circuits, we've met the new bosses, and we've seen the crazy sandwich boards. But let's bring it all home and talk about why any of this actually matters in the real world. This table really sums it up perfectly. The electrical design is basically the same across all the models, but the physical structure is worlds apart. The base iPhone 13, a simple single-layer board with direct connections. The Pro models, a complex two-layer sandwich that needs an interposer and relies on those test points for any kind of diagnostics. And these physical differences change everything about how these phones are designed, built, and, of course, repaired. And here it is, the whole journey on one map. You can see the power leaving the battery. It splits off to our newcomer, the Boost IC, and our manager, the Charging IC. That Charging IC is also talking to the battery. And from there, all that nice, clean, conditioned power goes to the main PMIC, which, runs the whole show. It's a complete system, and it's really elegantly designed for efficiency. I just love this quote that was found in the source document written by a technician. Test point friends, who are the best repairmen? Let us see the whole picture of the circuit before making a big mistake. It's just a great reminder that these design decisions aren't just abstract ideas on a computer screen. They have a massive real-world impact on the people who have to keep these incredibly complex devices working. And that really brings us to our final question. This trend, this move towards more specialized chips and more densely packed, layered boards, it clearly makes things more efficient. But what does it mean for the future? How is this balancing act between performance and complexity going to shape the next generation of our devices and the chances of us ever being able to repair them?